G'day, my name's Tim Trudgian, and my paper is called A New Upper Bound for the Argument of the Riemann zeta-function along the critical line, Part 2. My paper seeks to find a better estimate for the explicit error term in the number of zeros of the zeta-function up to a certain height. Most papers proceed as follows. We try to bound the zeta-function on the line sigma equals a half, and we know, for example, that on that line zeta of a half plus it grows no more quickly than t to the 1/6 log t. And we know a lot more than that actually. We know it grows no more quickly than t to the 32 over 205 plus epsilon. But we have good explicit estimates for 1/6, so we'll stick with 1/6. So we can bound the zeta function here explicitly. We can also bound the zeta function here explicitly. It's O of 1, and we can write out what that O of 1 is. So hence, by the Fragment-Lindelof principle, we can draw a line here, and via a convexity argument we can say the zeta function grows no more quickly than points along this line for sigma between a half and 1 plus delta. But notice what happens here. When sigma equals 1, this bound that we're given here is some non-zero number. But we know the zeta function is O of log t along the one line. That means that this line here should be very close to this axis. It should be within epsilon of that axis. So we're throwing a lot of information away. So what I tried to do was get an explicit bound not from a half to 1 plus delta in one go, but from a half to 1. That meant I needed an explicit bound on the zeta function on the one line, and then another bound from 1 to 1 plus delta. So you get the bound in the entire strip by going from here to here and then from here to here. And then you don't get this waste, this overshooting the mark when sigma equals 1. That's it. I hope you enjoy the paper. And I also hope you enjoy the upcoming Ashes series in Australia. Thank you.